G'day, in this video we're going to be focusing on circular motion and orbits. This video introduces concepts that are going to help us to cover dot points 5.3.2, 3 and 4. We're continuing to build our understanding on how gravity determines the motion of planets and satellites, particularly how gravity causes circular motion. As such, our key focus will be implementing concepts that we've learned about gravity, as well as circular motion, and combining both concepts together. So our key learning intentions today are to apply circular motion concepts to objects in orbit, and then begin to introduce some of the differences between geostationary, geosynchronous, and low Earth orbiting satellites. The first thing that we're going to do today is combine Newton's law of universal gravitation and some of the circular motion formula that we have looked at already. This will require three equations. First off, the law of universal gravitation, as well as our equation to calculate force and centripetal force, and our formula to calculate for circular velocity. By combining these three equations together, what we'll end up with is this equation at the bottom, which when completing calculations allows you to relate variables which exist in the universal gravitation formula to the period of an orbiting object. The first thing we're going to do is combine the universal gravitation and centripetal force formula. The reason that I'm doing this is because for an orbiting object, the force which is causing the object to orbit is the centripetal force and is solely caused by some sort of gravitational pull. Once we rearrange to solve for g, what we find is that the mass of the object that is having gravitational force applied to it is cancelled out, as well as one of the radii being multiplied on the numerator. From here, I'm going to sub in for the circular velocity of the orbiting object. This is going to give me a new expression. What we see here is a formula which includes the gravitational constant as well as 4 pi, both constant values, but three key variables: the radius between the two objects, the mass of the object causing the gravitational force, and the period of the object orbiting around it. This formula effectively relates all three of these variables, and whether you use this formula or the rearranged version that we see at the bottom of our data sheet, doesn't really matter because you're going to have to rearrange to calculate for those three variables anyway. Just for clarity's sake, I'm going to move 4 pi and m over to the left-hand side to show you that the formula that I've come up with here matches the formula which is in your data sheet. What we can begin to do is apply these formula to different types of orbiting objects, whether they be planets around stars or satellites around planets. One type of orbit that we are going to be focusing on are geostationary and geosynchronous orbits. These kinds of orbits are for satellite objects which match the angular velocity of the Earth. In other words, as they orbit around the Earth, they match the Earth as it rotates on its axis. At least that will be the case for the geostationary satellite, which is able to follow the equator. For a geosynchronous satellite, it will still rotate at the same angular velocity of the Earth, but because it's following a path that is not perpendicular to the Earth's rotational axis, it will still cover different parts of the Earth at any given time. The other type of orbit that we'll look at is low Earth orbit, which is quite close to the Earth. Now, in order to maintain orbit, these objects need to be traveling much, much faster than the angular velocity of the Earth. In fact, objects in low Earth orbit are still actually in the Earth's atmosphere, but in a place where the air is significantly thinner. Something else that's important to note is that as you move your satellites into orbits that are further and further away from the Earth, the signals that they can project or receive widen out quite largely. Now, in terms of understanding these orbits and why they exist, This is something you're going to be unpacking a little bit more as an in-class activity. Thank you very much, everyone. In the next video, we're going to be focusing on applying Kepler's laws of planetary motion to some of the concepts that we've already learned in this inquiry question. But until then, have a good one.